components of the monastic landscape for warrens and the water meadow. The warrens are England's most common archaeological evidence of rabbit farming. The warrens provide housing for rabbits which struggled in British winter. Although the church disapproved of hunting, the monastery was still awarded the right to free chase, and we know that it persecuted poaching on this free chase. We can see from the map on the left that the warrens don't appear to sit within the Lord Wharton's Deer Park, which was constructed in 1560. Moreover, they don't appear on the Lothar estate plan of the Deer Park from the mid-16th century with 18th century additions, all of which would suggest that at least part of the 63 warrens present were constructed under monastic ownership. Several factors had to be considered when picking a suitable location for warrens. Rabbits struggled to make their burrows on flat ground and required well-draining loose soils. Additionally, during the 12th century, there was a lot of competition for high-quality pasture, and the destructive potential of rabbits to arable crops had to be considered. According to these factors, rabbit warrens are often enclosed on poor-quality soils such as moorland and typically on slopes. Water meadows were primarily used to increase a field's productivity by lengthening the growing season of the medieval period. These were water management systems that collected, used, and discharged water over target fields. This encouraged early grass growth by allowing additional farming growing seasons. Depending on the complexity, water meadows can be classified as simple dams, catchworks, and bedworks. The Scandal Beck runs along the southern edge of the meadow, and while a leat is visible to the northern edge. The leat is a major indicator of the patchwork system, which carries water along sub-parallel to the slope's contours before overflowing to flood the gutters. As both features are visible on spectral imagery, it's fair to assume that they would be detectable by automated approaches. Much of the current success with machine learning is focused on visually distinct, prominent features on relatively even terrain. Therefore, the project and the features were chosen to test if the success already seen in other research could be replicated in a more unfavorable setting. The water meadow is in a relatively flat basin and comprises features of varying prominence. In contrast, the warrens are mostly located on steep slopes and are not hugely prominent, especially compared to nearby monuments. The dataset to train the models was created new for this project, and the mapping was carried out following the standards outlined by Historic England. Conversely, blue and yellow have both been chosen to represent banks and ditches, as they can be easily seen on all the figures. The data contains 63 warrens and 264 features comprising the water meadow, which were used to train the model. The models were trained on 80% of these data, while 20% were kept to test the model's accuracy. The training data was created using segmented visualizations through ArcGIS. Pixel-based approaches like support vector machine classifier require polygon training data selected using the segment picker function in consultation with known mapping data. Object-based approaches such as forest-based classification and regression use a different labeling methodology requiring the training data to be stored as points, so a second set of training data has to be created with points placed at the center of the warrant. DEFRA supplied LiDAR data at 1 meter resolution, which provided a DTM representing Burr Earth elevations. 16 visualizations were generated from this DTM. Discussion here focuses on the clearest outputs, positive openness, local dominance, changing concavity, and mean curvature. These visualizations were segmented, grouping pixels in close proximity and of similar spectral characteristics. The models can then extract features from the image using these objects. Additionally, geomorph on landforms was used for a comparison. This project used 4 single variable-based approaches: set null, con, random trees classifier, and support vector machine classifier. Set null, con, and random trees classifier did not perform well. SVM is a machine learning approach that provides robust predictions to new input data. Standard SVM identifies the optimal separating hyperplane between two possible classes already assigned to a labeled dataset. This allows SVM to produce a highly accurate prediction on relatively small training data. Automated approaches are recommended to use training data sets of at least 100 features. Although the training data only contained for 50 warrants, SVM works on smaller data sets. Additionally, whilst SVM is capable of multivariable analysis, it also works on single variable, as was done here. This image shows the model created to run SVM in ArcGIS. This took both the LiDAR visualizations and the training dataset to train the SVM classifier. Simultaneously, the visualizations were segmented. Both outputs were then used to classify the raster, creating a raster file. All LiDAR visualizations were input into the model, but local dominance works best for this area. The multivariable object-based approach used was random forest-based classification regression. This creates a model by applying bagging or bootstrapping aggregation technique. Each decision tree is generated in parallel from a randomly selected portion of the training data. The variables and the observations. The random forest generates a classification score calculated on the aggregate results of the individual trees. This can be used to generate a probability map. Random forests also provides information on the level of importance of each of the variables. This allows the researcher to remove less critical variables, which, if done correctly, will increase the accuracy of said predictions. Forest-based classification regression is an adaptation of traditional random forest algorithm. The predictors can be used for categorical and continuous variables. This methodology requires a more refinement before verifying the results. The output raster was converted to a polygon data tool, and an area-based candidate query was carried out to filter by size and shape to help identify candidates within the warrant's correct range to reduce overfitting. Both SVM and forest-based classification regression provided useful results. The size of many of these channels with visual mapping data. We can see the model identified the slope running parallel to the lead as part of the feature and several other anomalies, particularly identified outside of the water meadow's boundaries. The model accurately identified the extent of the lead and the river that form vital parts of this feature. This might represent the clarity of these features compared with the channel in the visualization used. This model requires extensive trial and error for variable selection to output accurate results. The model was run 8 times to find the variables that generated the most accurate results. It was reduced from right to left. For this model, every variable with an importance below 0.15 was removed. The results of this model for the warrens in light grey. The model accurately identified 91% of the warrens. However, there was a significant degree of overprediction. A substantial portion of the overprediction was associated with visually similar archaeology. The warrens are comprised of banks surrounded by ditches. Hence, the model struggled to distinguish them from ridge and furrow alignment, which can be categorized as a series of parallel banks and ditches. For features such as these, it might be more beneficial to use an algorithm that detects banks and ditches rather than trying to identify individual features. As stated, the results were filtered by size and then shape to try and reduce this overprediction. The dark grey represents the initial filtering by size. This significantly reduced the amount of overprediction, but reduced the number of warrants accurately predicted to 48%. The final filtering by shape can be seen in red. This further reduced overprediction, but reduced the number of identified warrants further to just 29%. This model was not run for the water meadows due to constraints. The SVM results demonstrate that single variable automation is better suited for specific monument types, but not others. This approach has worked well in identifying water meadows' ditched features, as those are moderately uniform in shape and dimensions, with high contrast to the relatively flat and uniform geology. Whilst for warrens and water meadows' banked features are uniform in shape and size, there is little contrast between them and the highly varied geology on which they are found. This might explain why single variable SVM could not identify the warrens' banked features. SVM's dependence on one variable means the results cannot be aggregated across inputs and depends on a single information set. Other projects have solved this problem by using higher resolution data. This area is covered by 1 meter resolution LiDAR, and all these features are significantly more prominent, so the resolution might not inherently be the problem. However, the components of the monuments within the training data were often far smaller, so a high-resolution dataset might be able to better define the monument components compared to such things as ridge and furrow. A good way to increase the efficacy of automated feature detection is to move from single variable model to a multivariable model. These models can carry out the same but different processes but on multiple inputs. The model calculates the probability value for each variable, which can be tested against others to produce a final probability. This can either be done as a mean value, or, as with forest-based classification regression, each output value gets a vote. This makes multivariable analysis more powerful as it removes much of the noise. This allows them to detect smaller, structurally homogeneous features. As such, whilst SVM could not detect for warrants, forest-based classification regression could detect between 91 and 29%, depending on the level of further cleaning. Implementing additional, more varied inputs could increase the reliability of both these models moving forwards. Prior studies have proven that additional objective criteria, such as roundness, compactness, and shape, are effective variables. With more training on a wider set of variables, these could be implemented for projects as they are generated from the existing DEM. This study relies mainly on publicly available LiDAR, so incorporating a multi-sensor approach through multispectral or satellite imagery also has the potential to increase the model's accuracy. However, unlike objective criteria, multispectral imagery comes at a financial cost that has to be considered and is outside this project's scope. The training data size might also contribute to the false positives combined with the geology and construction. Typically, using at least 100 samples in a training data set is advised. There were 211 for the water meadows SVM, which worked effectively. However, the warrens only had 50. Whilst both Kramer and Orengo saw success with 22 and 25 samples respectively, their target sites were well defined, allowing automated features to detect them far easier. Using Historic England's aerial mapping Explorer data, we could increase the size of this project's training data in the future, and I promise this wasn't a paid ad. The reception of machine learning and archaeology and automated feature detection can be understood in the framework of Gartner's hype cycle. The model follows the evolution and implementation of technologies as they pass through consecutive periods of peak, disappointment, and redemption of expectations and possibilities. In manual practices, archaeologists must have an expert knowledge to identify features such as the compendium of monument types and dates. This approach introduces inherent biases towards the archaeologist's knowledge and expectations of the archaeology and procedures, which can lead to omissions and errors. The scholars who first tested approaches proposed that computers, as they can hold a greater number of known features and combine a larger source of information, would significantly reduce the archaeologist's input while increasing the accuracy of the output. The algorithm's issues could be attributed to human errors in programming rather than the technique's ability, so this period can be classified as peak expectation. The early 2010s saw a slew of publications that were highly skeptical of automated approaches that can be seen as the next step in the hype cycle, disappointment. This period of skepticism highlighted that every project is heavily dependent on local variables, leading to more regionally specific algorithms. In more recent scholarship, dependent on local variables, leading to more regionally specific algorithms in more recent scholarship. It was clear that automated analysis introduced a new set of assumptions and limitations while compounding some of the biases of expert knowledge on which the training data was still based. Indeed, automated detection requires expert knowledge of the area and the archaeology, in addition to machine learning approaches, arguably increasing barriers to entry. However, for the most part, these new biases are still explicit and repeatable. Scholarship has recently accepted these criticisms, changing the aim of automation from replacing manual evaluation towards providing additional tools, transitioning into redemption of expectations. As the forest-based classification regression results show, automated feature detection involves an essential trade-off between the number of features detected and the percentage of correct features detected. In this model, the initial algorithm predicted between 91% of the warrants but greatly overfitted the data, which was reduced with further processing to 29%. Therefore, it would be inappropriate to rely solely on automated techniques. These can still be used to confirm potential sites and speed up the mapping process by identifying over 1/4 of monuments. The degree to which archaeologists have overpromised the potential of automated feature detection is also highly reliant on the project's goals. Most recent studies regarding implementation have targeted a specific monument type, typically over areas of hundreds of kilometers squared, with possible additional research aim of understanding site distribution patterns. Although it takes time to develop and learn automated techniques, machine learning can be cost-effective on projects at these scales where the accurate mapping of the entire historic environment is not required. This is because once the algorithms are implemented, thousands of square kilometers can be surveyed at the speed of a computer's processor, significantly reducing the archaeologist's burden. However, if we look at projects such as the endangered archaeology in the Middle East and North Africa or historic England's aerial investigation and mapping, the aims are very different, and the efficacy of automated approaches will change if implemented. AMENA's stated primary aim is to rapidly record and evaluate the status of archaeology in the MENA region. Similarly, HE aims to identify, record, and improve understanding of sites and landscapes. These projects both target a range of monuments across all periods of human history on a national and transnational scale, making variations in regional geology and monument type more profound. This means these projects would require many algorithms to accurately and efficiently predict target archaeology, making this approach less effective. However, one should not exclude the benefits of automation, as an algorithm that detects and records the locations of possible ditches and banks over such a vast area would still reduce mapping time. This paper supports the argument for automated feature detection, emphasis can, be a waste of resources compared to traditional remote sensing techniques when surveying smaller areas. After testing 5 automated approaches with 16 variables, only 2 produced usable results. Whilst both images here show water meadows, ditched features, the geomorphon visualization is better defined by the archaeology on the ground and has already identified a greater number of banked features, shown in red. The LiDAR visualizations are able to display yet more detail. Therefore, the automated approach has produced a less accurate detection than the manual approach. The same is true for the warrant. Therefore, automated approaches cannot yet pick up the same subtleties in remote sensing data as the human eye. This paper has demonstrated that automated feature detection can and does work as long as data and the models are chosen correctly. Most significantly, automated techniques reduce bias introduced through empirical reasoning. Additionally, automated approaches are especially useful for surveying large areas for a single well-defined feature. Thus, these models could be applied nationally with a larger training data set.